we're going to do a bit of problem solving and mystery solving today. So geology is always a bit like being a detective. CSI Geology, if you will. So our standard geologist, we've got here. And we're going to look at lots of different pieces of evidence across all the sciences, biology, chemistry, physics. That's the point of geology. We call it a really holistic subject because you take your skills from all the three main sciences, put them together to try and solve problems. So we're going to try and deal with one of the biggest mystery problems that has been puzzling geologists for 50 years or so. The thing is, though, like any good mystery story, some people already know certain bits along the lines. So if you do know certain bits or have heard certain little bits of evidence before, keep quiet because there are new things. You'll discover some things you wouldn't know before today. And don't shout out any spoilers. It's definitely, however, the butler dinosaur, as we see over here, he's definitely not responsible for it. So it's not like an Agatha Christie murder mystery this time. So any CSI detective or any crime scene officer would want to identify and talk to witnesses if we have a crime that's gone on. Problem is with geologists, we're interested in problems that happened a very, very long time ago. Longer than any of you are old in this theatre, probably times that by 100, and we still, even if we went back to your ancestors, they wouldn't know. So then we've kind of got to skip the witnesses and try and find something else to use as a witness. So what usually do we have when we're solving crimes? What about a crime scene? That's got to be around. Let's go over there first. Our crime scene. Anyone thrilled to see our crime scene? No, not mine. To a geologist, they'd be jumping for joy. This is really exciting for your standard geologist. So what we're seeing here is a rock face. And you see we've got a band here that's quite light coloured and white. We have a band here that's thinner and very dark coloured. Another band here that looks sort of similar to this band, but is a different colour. And we'll get on to each of these types and what they actually mean. So then how can we interrogate our crime scene? How can we actually get some information out of this? So there are a couple of rules in geology that we can use. And one of them is the law of superposition. And this says if our rock face has not been deformed or changed, then the oldest rocks are going to be on the bottom. So a nice analogy is if we're looking at a house. So imagine if someone asked you to find out things about our house. What bricks were the first bricks to be put when we were starting making the house? Shout out, people. That's fine. Yeah, that's right. The ones at the bottom. These ones. And so then the next oldest are going to be the ones above, keep going, and the final ones are going to be the ones at the top. So this is one of the very simple concepts that geologists use all the time to work out which rocks are older than the other rocks. But of course, I said the rock mustn't be deformed or changed. So then how's the geologist to know if it has been deformed? Well, go back to our house. What do we see? Well, what's wrong with our house? Anyone?
Upside down.
Yep, our house upside down. And you can tell this, hopefully, because you've noticed that things like the windows and the doors are the wrong way up. This is exactly what geologists look for in our rock type. We look for things called way up structures. So that enables us to say, oh no, this rock is in its original position and it hasn't changed, it hasn't been twisted. So this means we can go back to our rock area and we say, oh look, this rock is on the bottom. Our way up structures tell us that this is the correct bottom, so this is the oldest rock. Still sticking with our house analogy. So we have some lazy builders when we're putting this house together. Whereas most builders should be able to do lots of different jobs. Our two builders, Wendy and Bob, can only do one task each. So Wendy puts the bricks down. So she lays the first layer of bricks. But the thing is, if Wendy just kept on laying bricks over and over again, we wouldn't have a very stable house, would we? You could just push the bricks and they'd all fall over. So this is where Bob comes in. Bob is a builder that only knows how to lay cement. He's still in training, but he also loves cement, so that's what he's going to specialise in. So then if you are a geologist and you look at your house, you can see that, well, you know that Wendy lays bricks, so Wendy must have been working to put the bricks on, but then she must have stopped. We have a change in our environment, a change in our system, and something else comes along, in this case it's Bob, that puts the cement down. But then, of course, the cement stops, and then we're back to Wendy, laying bricks over and over again. And so geologists can use these techniques as well when we look at our rock face. So this becomes a little bit more interesting to a geologist because I mentioned earlier, we've got different rock types. We've got 3 clear different bands. Our oldest rock type here is the white one. We're calling it limestone. But then we have another band that's different to the limestone. So we have a change in the environment, a change in conditions that means that this middle band, that's sort of a grey made of clay as well, that's been laid down. But now we see we've stopped laying that clay down and we've got the pink limestone on top. So we've got a good story already out of our really boring rock face. There's a lot more we can get out of it. So we've been laying back and having a look at our rock face. Let's kind of zoom in and have a look. So geologists, when we're taking a closer look at the rocks, we like to look for things called fossils, particularly zone fossils. I've got a few examples here. Hopefully. And these are real fossils, and they come from the UK as well. So these are fossils known as ammonites. And zone fossils evolve really quickly, so that means they change over millions of years into different species. And a geologist can look at a zone fossil, like an ammonite, and say, oh, I know whereabouts in time this ammonite was alive. It's a bit like if you're a history teacher and you go to look at a castle, you may know, oh, that's definitely a medieval castle, and that wasn't built in the current reign of the monarchy. You don't know exact dates, and you couldn't say this castle was built on the 7th Tuesday of August, but you can definitely know a rough time period. So some other zone fossils we'll look at to compare. For example, we have some of our shells, but then we've also got a more prehistoric shell type, which I'll put next to it. Can anyone see some big differences between our 2 types of shells, zone fossils? Yep, you at the back in the blue? So you've got this one that's really large, yep. You've also got some markings all the way around, yep. Any other differences between our shells? Are you there?
Lines on the big one are further apart from the smaller one.
Yeah, so this is what geologists do. We've noticed that, see these lines spread out quite thickly towards the end. This one, not as much. So geology is all about observing and essentially common sense in a certain level of saying, yes, I definitely see this. And from this, I'm now going to try and find things out about the environment. So, if we take a look at our rock face with our microscope, we see these types of fossils. And these are called forams. Now, forams live in the ocean, and they're tiny, tiny. See that we've got a scale here of just 1/10 of a millimetre. So we're definitely going to need a microscope to see these, so I can't have them on show. But we've got lots of different types. So we've got one here, that looks like it makes of loads and loads of different plates, all laid on top of each other. We've got some here that look like they've got lots of bubbles and are quite cylindrical in their shape. We've got some weird ones going on over here. But these forams we see in our oldest rock, in the white limestone. And so we'd expect them to be preserved throughout the rest of the rock face. But this is where something strange happens. In the top pink limestone, all the forams kind of look the same as each other. We don't have multiple different species of forams. You see they're all the cylindrical kind with lots of bubbles on. Some of them are slightly more circular. But you don't have the strange diversity that we've seen earlier. So what's gone on? This represents some organisms that were living at the time of the white limestone. This represents organisms that were living at the pink limestone. So why don't we see our really strangely shaped forams anymore? They've vanished, guys. They've gone. And it's quite likely that we'll never see them again. So that they've gone extinct. So something has happened in our rock face in between our white limestone and our pink limestone. It might be represented by that tiny, thin, black band of clay that we see. So let's try and actually find out an exact date and pinpoint when this is, when this happened, and see if we can use some other evidence to work it out. So what we're going to need to do is some radiometric dating. We're going to look at some elements that we find in the rock. So a couple of years ago, scientists discovered that elements give off particular signals depending on what element they are. So, for example, carbon-10 makes the signal like this. Can everyone be some carbon-10 for me, please? Fantastic. Keep it up, carbon-10. Doing really well. And so as a scientist was looking at the carbon-10, watching it, keep waving, guys, keep waving. You're still carbon-10. You're going to be a little while being carbon-10. They suddenly saw that the signals changed. So can I get everyone that's this side and across to stop waving as carbon-10 and start waving like this? So everyone look around the lecture theatre as well and see who's being carbon-10 and who's not carbon-10. So we've got about half and half. The signals have changed. This is odd. And then the scientists kept observing, and then they found that, say, everyone from this area and up. Can you do the slide hands, please? Brilliant. And we still got some carbon-10. We've got this strange other signal going on. You wait a little while longer, kept observing. And then we have this group this side. Swap the side hands, please. Brilliant. So if you look around, most people are doing a different signal, not the carbon-10. We've still got a carbon-10 group here. And then this group, can you stop waving? And can you do the sides? And then eventually we've got a tiny amount left. And so the remaining carbon-10s, now can you swap? So we've now got a sample that we've looked at from our rock that's all making a completely different signal. Right, you can all stop now. Thank you for that. I hope you enjoyed being carbon-10. So what you guys have all demonstrated, something called radioactive decay. Some elements, like carbon-10, are not stable, and they would rather turn into something that is stable. So it turns out this sign is the sign that boron makes. So what happens is the carbon-10, over time, turns into boron. So why are geologists interested in this? Well, it turns out the element that's unstable, carbon-10, has a probability or a chance of turning into boron. And that chance stays exactly the same. If you heat a rock up, if you cool the rock down, if you twist it, fold it, bend it, all the things you normally think that would change how a reaction works, doesn't happen with things called radioactive decay. And so we will see that on our graph. Now don't worry that it's a graph, guys. We're going to talk through it and explain it. So there are other elements that do this as well. Things like potassium turns into argon over time. But so let's take this curve. This was our carbon-10. That's all of you in the lecture theatre up here. But after 20 seconds, we did just now, we had half of you all turn into boron, and you decayed. But the thing is, changing every 19 seconds is not very useful for geologists. We're dealing with really, really, really big times. And if we had something that changed every 19 seconds, it's going to be gone by the end of the day, let alone geological time. So this is why we use potassium. Potassium has a half-life, which is the time it takes for half of the sample to change signal and become the element argon. It's about 1.3 billion years. So that's 1,300 million years. So it's going to be around for quite a long time. And this has enabled us to try and work out our exact date of our rock face, so we know the exact time that our mystery or our crime has taken place. So I think it's time to travel in time and find out when this is. We had the date from our isotope dating of 66 million years ago. Now, for most of you here, that will probably mean just a very long time in the past, before your great-grandparents were around. So we're going to travel back in time with the help of a geological time scarf, try and work out what was going on when in the Earth. So if I can have my assistant Simon stand at the top. And I will need some volunteers in a minute, so get prepared. Right. Geological time is going to start at the back of the lecture theatre. If you could hold that. And just, thank you. So, this is the beginning of, sorry, hands down everyone, I'll call for volunteers in a minute. Thank you for being so keen. Right, this is the start of our Earth has formed, the beginning of our solar system. we've essentially got a huge amount of molten rock. It's all sort of lava. We've not got any continents formed or any water on the Earth. So this stays for as long as we have the red part on the timeline, which, as you can see, we keep going, works out to about halfway down the lecture theatre. By the time we get to yellow, we've got water on Earth. So we haven't got anything living. So if you're interested in fossils or want to go on a prehistoric zoo trip, it's going to be a bit boring. It's just going to be full of volcanoes. If you're into volcanoes, visit them. So we have travelled back from 4.6 billion years ago. And hopefully, the end of the yellow, we will have travelled this here, this change from yellow to grey, marks the sign of 2.6 billion years ago. Can I have a volunteer, please? Something amazing happens. You were very quick in the green. You'd like to come down? Something fantastic happens around this time. Right. Can I get you to hold this part of the scarf? And can I get you to hold this up very high? So this here is a single-celled organism. We have a really, really basic life that's happened. We don't have anything complex, no plants or animals yet, but one cell is alive and creating energy. So we have single-celled organisms for still a very, very long time, as long as the brain is stretching. Another billion years or so. In fact, 2 billion years. Keep going. It takes a long time for single-cell life to essentially tidy up the vast single-cell life and produce interesting multicellular organisms. All the way up here, we are now 500 years in the past. So if someone like to represent multicellular life in the blue there, you want to come down? In fact, what we'll do, we'll look back on ourselves. We'll come down here, so it's easy to see the next part. Just like that here. So you are representing the start of multicellular or complex life. So then once we start life, 500 million years ago, it starts getting interesting. At a period of time where we have lots of fish, marine life, the oceans. About here, we have our first plants. If someone likes to be a plant, you were in the grade, you were very quick. Come and be a plant. So our plants emerged about 420 million years ago. So we're still not close to our 66 million years ago at the time we got from the data. Can you just hold the scarf as well? So life starts to do complex things now. And you will know what's coming next. So dinosaurs evolve around the orange part of the Triassic. You in green, would you like to represent the start of dinosaurs? Most of the dinosaurs you'll likely see at some of the Natural Museum, including a dinosaur called, anyone know a really famous Cretaceous dinosaur in the blue jacket at the back? Sorry? T-Rex? Tyrannosaurus Rex? Fantastic. Would you like to come down and represent Tyrannosaurus Rex? And so what most people don't realise is that dinosaurs still alive today. The things that we see in the back garden and that we often feed, T-Rex. That's represented T-Rex probably about here. Very much. Way too T-Rex for everyone to see. The things we see in that garden, we often feed the birds, are also dinosaurs. So they are descended from things like T-Rex. Also, they have all the same different characteristics, such as having an ankle bone that cannot rotate, having hand bones that have a particular shape of the wrist. Those are all key dinosaur characters. And birds have them too. Therefore, birds are dinosaurs. And this is around there. So T-Rex appeared about 68 million years ago. So we've only got a small bit of time left. So let's get around to the next bit of time. So next bit of time, this area here, we see the uprise of mammals. So who would like to represent mammals? So in the red, and so this is where we start to see a lot of creatures that you recognize. Things like elephants, giraffes, lions, and we'd like to show now the students. We have our characteristic I can't even represent the mammal. So now we're starting out here. And then finally, humans are mammals. In the blue, very keen to represent humanity. And so we see this one single thread of pink represents the time humans have been around since time of policy. That's sounded very proud of you. Thank you. So this single thread for humanity is actually too big for this geological timescale. And this gives us a scale. We consider how much grey and yellow, going back to our single-cell organisms, and all the way back to red, where the Earth first started. Humans have been around for a blink of an eye. Dinosaurs were definitely with the time they've been around. From the start of the Triassic, 250 million years ago, to the birds around today. So, we had our date 66 million years ago. And we saw that T-Rex was around 68 million years ago. So shortly after is where we're looking at our mystery, when that occurred. Now, hang on a second. Who's seen a T-Rex in the back garden? Anyone there? A real T-Rex. But it's not. Along with other dinosaurs, Diplodocus, Ankylosaurus, Triceratops. What's happened to them? We've all seen something strange happen with our forams as well. They've got to be really diverse to compete with superior. Maybe the two are connected. So I think we should go back to our rock walk to try and see if we can find more evidence. People that represented key moments in time, thank you very much for volunteering. I'd just like to drop the scarf back to the seats. Thank you very much. So, for those of you that are really keen on chemistry, we're going to get our chemists involved. So my next one, Jim. So when we looked at our really thin grey line area, we saw a particular element being present. This was pretty strange. This element here is called Iridium. It's type of metal. It's exceptionally rare on the part of the Earth we live on, the outer crust. And this is because Iridium reacts very strangely with iron. Iridium loves iron. It wants to be its best friend all the time. Doesn't want to be separated from iron at all. And so when the Earth is forming, up in the red parts of the star, we see that there will be iridium bound to the iron and went into the core. And the core of the Earth is an iron-nickel mixture. And so all of the iridium left the surface and went into the core. Here's our iridium in our rock face. This isn't right. We've seen a huge amount of iridium in our rock type. It's got to come from somewhere. It's almost like we've taken a planet and maybe broken it up and shattered that on our Earth. So where can we find random bits of planets? Any ideas? Shout out, guys. Outer space. So yeah, outer space So, can I have 3 volunteers, please? Not one. You in the grey, you in the pink, and you in the blue. That's my next part. And I think we need 1 more volunteer. My demonstrator Simon at the back. You can come down and volunteer. Yeah, you look like you're full of energy. Brilliant. Right. We are going to try and model the solar system. So, do you like to be the sun? The centre of our solar system. So you want to go on the big rays. You are the sun. So, sun and the earth are a distance of 1 astronomical unit away from each other. And so, if we scale this up to try and put an electric data, you would like to represent the earth, which is a lovely blue shirt. So the earth is for the water supplements. You should stand about here. So 2 meters away is the distance between the earth and the sun. Now, there are some several planets, and there's one image. So, are you able to go almost to the back of the electric data and be a big, strong planet Jupiter representing the dogs? So, this is our journey from the sun to blue Earth to Jupiter at back. Jupiter, can you give me a big wave? Fantastic. So, asteroids, where do they come from? They come from a region called the asteroid belt, which is in between the Earth and Jupiter. Distance approximately. Okay, everyone in this row, would you like to wave at the asteroid belt? This is the asteroid belt. And so, this is about 6 meters difference away from our Earth. And so this is where most of our asteroids, our big heavy rocky bodies, come from. What about something else? Comets. Simon, would you like to know comets?
I'd love to.
Ah, brilliant. I hope you're on YouTube. Yeah. Right. To get the scale of where comets come from, something called the Oort cloud, which is rather far away. So we wanted to try and fit some electric data. We're going to need you to go for the job. So Simon, are you ready to run all the way to Germany? There we go. And it's not just the close part of Germany, the really furthest part of Germany. You can run to Spain. This is how far out the Oort cloud is. And as gravity from our sun, it's still not affected by comets. I don't think Simon's coming back for a while. So thank you to my volunteers. Round of applause for you. And so we have our comets, we have our asteroids. Which one's more likely to cause this strange Radiometric? Comets are made up mainly of ice and frozen gases. The nucleus, which is this region here, is about 2 to 3 kilometers wide. And the tail part, you see, is what happens when the asteroids. Sorry, this is the tail part, so we see when the comets come close to the sun, they heat up and start evaporating. And so the tail is just gases, almost burning off, disappearing away. But we've got ice in a comet, and we have gases in a comet. Don't really have any metals. So it's probably not our comet that causes this strange iridium. What about our asteroids? This is the third largest asteroid. And you can see it's got lots of craters. This is where other asteroids smaller than it have crashed into it. The largest asteroid is possibly the size of the British Isles. So these are bodies that are made of a mixture of metal and rock. Iridium is metal. These are, we reckon, formed. So quite likely to contain parts of iridium and parts of protoplanets that didn't fully form. And hey, presto, could this be our mystery solved? Have we got a massive asteroid that's crashed onto Earth 66 billion years ago? Well, we need evidence. If it hit the Earth, something so large, it would be a crater surely. And we found it. Yes, we have. So, the Yucatan Peninsula, which is around this part of Mexico, you can see from geologic surveys, this is the predicted area of the crater. Ginormous. Now hang on. We've got craters all over the Earth at this time of the extinction happened that caused our T-Rex and our Forams to die out. Did anyone just be like, alright, something in the sky, I should run over and stand underneath it? Hopefully not. Especially as America is surrounded by water, we've got pictures of the old country that like this. What happened was very unlucky. Remember at the beginning of the lecture, I said that there was limestone underneath the layer of black plate? So limestone is made up of calcium carbonate, which when under really high pressure, like meteorite, will vaporize and produce lots of gases all enter the atmosphere. So along with all of these gases, we've got a huge ash cloud created by this giant asteroid crashing down onto the planet. This quite likely would have caused a vapor cloud around the Earth, blocking out the sun, stopping plant life. Now, from our food webs, you stop plant life, you then stop feeding all of the herbivores. The herbivores die out, all the carnivores die out, and suddenly you have a whole ecosystem collapse. Hundreds of species are affected, die out, and are never seen again. So next time, just so we're understanding. It's always about, before you go, there's actually an awful lot going on in the Earth this 16 years ago. We had massive volcanism going on in India. 3 million years of volcanic eruptions. We had evidence of that. From lava and volcanic rock types we find in that area. We also see that a seaway, this is the Americas. You can imagine if you push all of these parts together, you get the shape of America. There was an ocean present at this time, just a peninsula where the impact happened. And our seaways are very effective at changing the Earth's climate. In certain systems, the seaways are closed down, such as the Forams current that happens near the UK, and suddenly temperature drops dramatically, and this affects the whole planet. So what we've actually got is at least 3 things going on, gradually changing the Earth, gradually changing the climate. And so overall, perhaps we have got a big asteroid impact that caused the trigger the extinction. We've also got this climate change that's happened gradually over a long period of time that has slowly caused the decline in our favourite dinosaurs. Thank you very much for listening, everybody. I hope you go home and find out more about things like Deccan Traps, about how oceans affect the planet, or also about space, asteroids, and meteorites, or anything you can inspire today, because there is so much interesting science that's involved in this, and geology is just like history celebration.